Okay, who is a developer here? Okay, at least some of them. So that's good because I will be speaking from the developer point of view. So for DBAs, this might be a bit like lightweight talk. So short about me. So the important thing is, for many years I used to work with Oracle database. We went through a lot of hard drive, disk setups and combinations and technologies, and then we arrived, I think the last significant one was the PCI card with 4 SSDs soldered onto that, and it had some special drivers and somehow managed to deliver really high performance on that. We did hundreds and thousands of financial transactions per second. I mean, with the latest technology, I thought, okay, so the performance side of queries is done. Then I switched jobs, so now I mostly work with a lot of cloud technologies, Kubernetes, and database is typically something that RDS, managed Postgres, database in the AWS. And so this talk is kind of inspired by trying to make live search query, so where you type some letters and it offers you results very quickly on the Postgres database. So, given the question how do I make my database work faster, the correct and typical answer is, well, it depends, but it's also not giving you any answer at all. So I will give some opinionated things that might not be fit for I don't know, maybe you will find some corner cases where it doesn't apply, or you will find some cases, I don't know, in 10% of cases it will not work, but I think the majority, this will be fine. So a bit of theory first, since all of you are developers. So I have this thing where I need to have some kind of mental model of the database in my head. So first, how the database stores the data. It stores it sequentially as a blocks on the disk. Typically a block size is 8 kilobytes. There are some variation of the size, but those are the blocks laid out. And so of course, if you want to find something, then it's linear complexity, and you just do a sequential scan of all the data until you find the things that you are interested in. Now, to have for a mental model, I will be using Python. So here on the bottom, so basically table data, you can imagine that this is a list of records. Again, sequential data structure, and that's it. Of course, it doesn't scale when you have larger amounts of data, so therefore we need some indexes. So for databases, the most popular one is B-tree index. So this is not binary tree, as developers like to understand. It's balanced tree, and again there are some small variations of the kind of structure itself and the algorithm, how it works. But the general idea is that this is a tree structure, and then if I want to look up some key, I'm trying to find where the key 18 is located. So the algorithm is that I start at the root node. I have to find the largest element that is equal to or less, the largest element that is less than or equal to 18. So on the root node, that element is 15. So given that one, I know that I have to jump to the next level. And on that level, the element that is largest one less than or equal to 18 is 17. So from 17, I get to the leaf node. And and then kind of on the leaf node, there are some variations. So there are databases like MySQL, which store the whole row data. There, in the kind of leaf nodes, there are, in Oracle, you can have index organized tables, but in Postgres, which is our current example, the data itself is it's called tuple identifier. So basically, it points to the physical block on the disk where the record resides. So in the end it's something like this. And yeah, in practice, so the Postgres has this feature that it never overrides the data. So it always appends the data, and then there's vacuum process, and after some running for a while, it kind of gets this basically randomized. So that's it. And if you want to have something like in a programming language, so I'm using the Python dictionary here, but I mean, it's not an exact example because it's in database, the index is a tree structure, but in Python, this is a hash map. But still, it will give you a good enough idea. So it contains the keys, and then given a key, it points to the index inside this table. So that's it. Now, a typical, what happens in when people define data structures in modern ORMs, so they define that, yes, I want index on all these columns, so they get the indexes created automatically, but still when you run the queries, they are still slow. So the question is, why database is not using the indexes? For Postgres, and also for the other databases, so what database is doing is that it tries to estimate, will the query run faster if it ignores the indexes, or it will run faster if it chooses some specific indexes. So for Postgres, I would say there are two significant parameters. There's the cost, how much it costs to read a single page from the disk in a sequential manner, like one by one. And the second one is how much does it cost to read a random page. And yeah, so the sequential is typically 1, and the random page costs the default value is 4. However, so it doesn't say that in the latest documents of Postgres, but I think in version like 12, it still said that this value 4 is chosen given this estimation that random page cost is approximately 40, but they assume that 90% of requests will go through cache. Therefore, they assume to kind of put this 4 as a default. There are some documentation that should suggest to put it as 1.1 for SSDs. And then there are some other cost parameters, but if you look at them, all of them are 0.0 something or 0.00 something, so they have like a very, very little effect on choosing which index and how to access the table. So now the interesting question. So these values are almost from the beginning of Postgres, so when it was running on the spinning disks. Now that for a database that is running in the cloud, like RDS, AWS, what do you think is the value of random page cost on the cloud environment?
0.9?
It's still 4. I mean, there are people like Postgres experts who argue that it should be kept 4 all the time. Their motivation is that there's like, it's not like a pure page access cost. It involves also what happens through the caches and what happens when I/O goes through multiple layers. So it has some hidden costs. I know that there's Alibaba Cloud, which actually has this random page cost set to 1.1, but for others like Google, AWS, and Microsoft, it's still 4. So it's a bit strange because it was the same value for spinning disks, now it's the same value in the cloud. Something is, either they do not mean anything at all or something is wrong. Okay, and why is it important to understand this cost? So let's say database decides that it will look up keys from 17 to 21 using sequential scan. So database has some statistics. It knows that it has 8 blocks, so it can estimate the cost, but just go with me. So we know that sequential access is 1. So if I have to scan through 8 blocks, database thinks that, okay, to find all the keys, it will cost 8. Now, if I want to go through index, So just a reminder, this is the index structure. And intentionally, I will ignore all the costs that the database calculates, how much it will cost to scan through the index, because index has additional like cost parameters and so on. We will focus just on the data. If database figures out that it will have to read some blocks after scanning the index, then random cost is 4. So it goes to one block, it already costs 4. It gets another key from another block. Then the next block, and already at this point it costs more than just doing sequential scan through the table. So, and in the end it's like twice as expensive. So it doesn't mean that this is the truth, but it's the way how database thinks and how it chooses which access it will take. And yeah, now that you know those cost parameters, then obviously if you just need to pick a single record, it's faster through index. Although you pay a random cost, it's like 4 instead of like scanning full table, so that's clear. Also, if you want to like read through the whole table, then sequential cost is cheaper. And then there's some balance in between, like what is the amount of records that is faster to be accessed through index than through full scan. And most like database materials say that this magic value X is a single digit, so maybe 2 or 3%, some say 5 or 7%, but it's like really small. And in the Postgres talk, a lot of it boils down to this sequential versus random access. So it's like, just based on those two costs, it's already 1 to 4, so it's 25%. And if you take into account the work that is needed to scan through the index, it goes down easily into the single digits. So that would be all nice and kind of correct, but yeah, database is often bad at estimating like the future, how much it will cost to access those keys. So therefore, it's sometimes database might think it will cost more when in reality it's different. And so given that, so let's go into practice. So I have a really simple model. So we have some kind of a person, a member has a name, and this is Django, so it says that for name it will create an index, so it's db index equals true. And then we have a related model, which is document. What's important here is that each document has a status, so it's one of these 3 possible values, also indexed, and we have some arbitrary JSON data. So this is the model. So that ends up creating these kind of tables in the database. So the main addition is that Django automatically adds the ID field, and it also creates the indexes, but I'm not sharing that. You just have to trust me. Indexes are there. So for the experiments, I created like these 10 records. Then I tried out some queries, and queries didn't work as I expected. So I created like 3,000 more records. So that's probably takeaway number 1. If you want to tune query performance, do it on something that is as close to the live data as possible to get the like same data distributions, same data volumes, and same hardware. Then the way in like Django ORM, if I have some query, I can it has this provides explain, which gives like the database prediction of how it will execute the query. So the first line is like Django syntax, so it's not that interesting. So we're just printing some like this Pythonic query language, and so what's common in most databases is that there's this explain, and then you can write down the query, and the database will explain how it will run the query. So here we are looking for a name that is equal to current long. So, and right now database says that it will use index scan, so it will access the table using index and using the index condition, so it will look up where name equals to whatever we have as an input. So this is the simple. I prefer a bit like more verbose. Output I typically use analyze. So again, in Postgres it says explain analyze, and then I do the query. So what this does, it actually executes the query. So be careful to not use it on a live database, you might bring it down. But the good thing is that it prints the actual time this query took, and importantly, it also prints the actual rows that were retrieved. So oftentimes, so here it's the same, but oftentimes you can see that the database predicted that it will retrieve 60 rows, but in practice it retrieved just once, so there's something kind of a bit screwed with statistics. Yeah, and it also prints out the actual times the query took. So, this is another example. So what I'm doing here, Django provides option where you can do like case insensitive search. It ends up as a query where you take an upper on the name column and compare it with the upper of input. So what happens here is that database is choosing to scan through the whole table. It's not using index. If you remember on the previous slide, we actually had an index on this name column. The reason it's not using it here because database is trying to find an index that matches this left side of filter condition exactly. So we do not have an index on upper, therefore it's like doing like table scan. And just to understand why it's doing that, again in Python, so if we create an index using like normal case names, and we want to try to look up something like using whatever the case is, it might be uppercase, it might be some mixed case, there is no such method on the Python dictionaries to look up by like mutated key, so therefore it doesn't work. So what I want you to take away, so if it says sequential scan, it means it's missing the index, and the filter line will tell what kind of index the database is looking for. And yeah, if you see index scan, then most of the cases you're probably good at using indexes. So with that in mind, let's look into other examples. So I had documents and I have document statuses. In the test data, I use status unknown for around 5% of the data. So just to make this work correctly. So the main thing for you to take away is that indexes work only if you have a positive expression. So typically it's equality. It also might work for less than or greater than. So if I want to look up documents with this specific status unknown, it's fine. It finds the index and it uses that. So no issue there. However, if you specify your expression as a negative, like negation, you say, I do not want to see documents and statuses valid and invalid, it will not use that index because it can't use it for negative expressions. So the thing here is, although by using like developer logic, you understand that the only possible document status value is unknown, it's not obvious to the database. So therefore, if you want to have something like this to work and to use indexes, you have to transform the query itself. Oh yeah, just why it doesn't work. So Python explanation, if you have dictionary with some keys, there is no method on this dictionary or map to ask, give me everything that is not these keys. So you can ask for a specific key, you can't ask for everything except these keys. Or you can actually do that, but it's like more like scanning the index, and so it's linear on the index and so on. So this is something you can fix as a developer. I have applied this in a lot of projects, a lot of places. So because you have more knowledge about the domain, you can transform all the like negation queries into like positive queries. So here, like a future-proof example, even for the cases where I might add new document statuses, I know which statuses I do not want to see. I construct the list of positive statuses, which actually I want to see. So then query turns out positive, and then it is able to use the index scan on the index. So we were missing some indexes previously. So remember this query where I want to do like kind of case-insensitive search, and it's looking for index. So the left side of the condition, it's looking for something that is upper on the name. So for this to work, I have to actually create an index that is upper on the name. So this is in Python, so as you can imagine in database it's not much more complex, so I just say that I need an index which is upper on the name. How it looks in practice, so index will be created for uppercase keys, and it will work, so in Python it would be like having dictionary where you uppercase all the keys, and then of course you can retrieve them by uppercase and kind of achieve case-insensitive lookup that way. And yeah, so created the index, it works. But now I want to do some live search. So live search, how to best explain it? So I type part of the name, and I want to database to return me some results that match this partial information. So the way in Python is to use iContains, so in Python Django. And this transforms into a query where upper on the column name is like upper on the inputs. So what's interesting here is it's not using any index. And we might think there's something wrong with the database because we do have index on the upper on the name of the name. So we created that before. But the thing, at least with Postgres, is that not indexes support the same type of operations. So it's instead of like using equality, it's using this like expression. So this is basically the like keyword. In SQL, it's just shorter form for Postgres. This kind of B-tree index doesn't support this partial lookup by the key. Like going back to Python, so if we have keys like that, we can get like retrieve elements just by the part of the key. So there's no such functionality. So what to do with that is that Postgres has other kinds of indexes. So it's like gin index, and specifically gin with the trigram operations. Again, so what it means in the Python that for any input string, it will retrieve three consecutive letters, all combinations of 3 consecutive letters. So here are the 4 car and long. So it's K-A-R, and so A-R-E, and so on. So it creates all those combinations, and then it will create index entries for these 3 letters, or trigrams, and they all point to the same kind of record. And then when you do the lookup, it will look up, it will do the same, calculate the same trigrams on the input, and we'll do a lookup with for all the inputs and combine the results and return it to you. So there's a lot of magic to make it work for like application developer. So in Python you have to include this contribution package for Postgres. Once you have that, you can create an index. So the Python syntax is really, really ugly for that. You basically say that you will need gin index. You will use specific operation on that, on the field of upper name, and you need to use the operation that is gin trigram operations. So this is like really ugly. I prefer this plain SQL one, so it's like really, really simple and readable, much more readable than the Python one. It doesn't stop there, so also in Python you have to create this trigram extension. So in Postgres it's just, you can type create extension PG trigram, so it's kind of included by default. You just have to create the extension itself. Once you've done this, it should work. But for this query, it doesn't. So it does the full scan of the table. Any guesses why? What's missing? No. It does have upper, it has upper. So the thing is, I didn't analyze the table. So it works from time to time, but if you're doing performance tuning, so whenever you change something, just run the analyze to have like up-to-date statistics. It might be that at this point, database didn't run the auto vacuum and didn't create the statistics automatically, so I had to force it. And once I did this, it works now, so it uses the newly created index, and it's all fine. So there's a curious thing. So this is using the case-insensitive search with upper. So what if I want to do this? What if I want to make it case-sensitive? Again, it doesn't work. Why it doesn't work? Because it doesn't have an index on the name that supports this specific like operation. We have index on the name, but it's B3, and B3 in Postgres doesn't support this operation. And if you want to look into Python, so we have created index like that for like this like operation, but of course you can it will not return any results, so Postgres just rejects this index. Now this is one curious case, and this is actually where framework shoots you in the foot. If I forget about the frameworks, I can use Postgres to create the index. So on normal column name, using these trigram operations, so index is created. I can then run the query using like. So it works because it's case sensitive. So it finds the index, so no wonders here. However, if I want to run case insensitive search, then for Postgres there's this I like keyword. And I like keyword translates to this fancy looking operation. So to tildes and a star. So it does case insensitive lookup for this specific index type. So in Postgres, each index has these kind of operations that it supports, and these specific trigram operations support case insensitive search. So I can do this, so I can have a single index and make it work both ways. And it might even be possible faster than this uppercase variant. But since I'm using framework doesn't generate I like operation, it just takes upper on the column and the input, and then but yeah, so if you're not limited by your framework, you can do some nice stuff. Now I had some more columns there. I had this JSON one. Let's back up a bit. So there are, if you look up tutorials on the internet, they tell you to create an index on the JSON column as a whole. Then you will be able to search into the whole JSON. I like to create specific columns on specific fields within JSON. So to get the indexes smaller and pinpoint what exactly I will be looking for. So here I am looking documents which inside JSON contain document key, document number key, and this key contains some numbers. And so it boils down to this query where upper is on both sides, and then database tells us that it's looking for this kind of index on upper, on the data, and so yeah, Postgres has kind of native support for JSON, so it can retrieve and work on the JSON field like this. So I kind of know what kind of index I need. So I created this index, and again, this is where this Django framework made me mad. because I found this by trial and error. It doesn't, the programming language doesn't complain, but it generates invalid great index statement, and it just fails with the Postgres. So this combination works. It kind of Django is happy, Postgres is happy, it creates the index. But it doesn't work. Any ideas?
You just can't that easily index just on.
No, the main answer is I did analyze the table this time, but there's something like very insignificant thing why it doesn't work. So you see, so this is the actual index created, so it's the upper line, and this is the query that is being run. If you pay close attention, there's either one or two greater signs. So in Postgres syntax, the first one, if you have just one this greater than sign, it means retrieve document number, like element name document number, and the value might be of any type. So it might be a list, it might be nested JSON, it might be an integer, it might be a string, it might be a boolean. It's whatever. And on in the actual query, with these two greater than signs, it actually, this is the operator that tells retrieve text field document number. So it's the same thing, but for database, because database is very pedantic, it's not the same. So because the first case, it can take whatever value and it will forcefully convert it to string, while on the second it will kind of, I don't know what even it will do when this is not a string. So I couldn't do this through Django, so I just created the index by hand. So putting these two greater than signs, and then it works. So not a big surprise. Now, I kind of have the indexes for the main columns, so now I have to put it all together. So in like real life scenario, we had something like 7 tables we were running queries through. So we type some text, and in whatever table we find the text, we show the main record. So I'm doing the same on here. So on the 2 table model, so I'm looking for members where either the name contains these 3 letters or the document number contains these 3 letters. So it's a bit like, if you haven't used Django, it might be a bit unusual for you, but I mean, in the plain SQL, it boils down to like simple join, left outer join. So on one condition or the other condition, and we remember that we just created indexes for both of those conditions. We created an index on the name, and we created index on the document number. And this is where kind of Postgres surprised me. So I worked with Oracle before. I don't remember seeing this with Oracle. So the execution plan here is a bit different. In practice, okay, so let's go through this one. So what it will do a sequential scan through member table. Then it will do a sequential scan on the document table. And then it will do some filtering, and then it will just join it based on the hash. So it will filter after it has read both tables into some, like, I don't know, while reading the data or when it's stored on temporary storage or so. But it's not using indexes. I know that indexes are there. They will work on individual conditions, but not here. So in our case, with the 7 tables, so it was even worse, because it was producing the product of all 7 tables, you know, like multiply all 7 tables, do it on the temporary storage, and then scan through, I don't know how many rows there were in the end product. But yeah, it was extremely slow. So turns out that, yeah, this is a Postgres thingy. It's kind of not well known, but it's acknowledged that, yeah, this is an issue. So how do you fix that? So this is Django syntax, but the main idea is that I first collect the member IDs for one condition, then I select from the document table and collect member IDs from that one. I do a union, kind of keep the just the original IDs, and then with those IDs I do like I query the records from the member table. So this is like really scary. So here, the most important thing. So it actually took like close to 4 seconds compared to, no, it's not 4 seconds, but anyway, it's like 4 or 5 times faster than the original one. So although this is like crazy complex execution plan, but it's much faster. Then it actually did use an index on the document table, and it also used the second index on the name. I don't know what's actually happening with the Postgres, but this is one of the cases, so this one is actually better. If you look here, so in the cost, it planned that it will get 85 rows from the document table. In reality, it got just 0 rows, so statistics are incorrect. So it might be that because of these estimations, Postgres decided not to use the indexes, but who knows. Anyway, with a much complex query that accessed the members table like 3 times instead of, I don't know, 2, it's significantly faster. And we did it even faster because kind of, if you think a bit about it, then you realize that you can retrieve like member ID from the document table directly. You don't need to join the member table to retrieve the ID, so because there's the member ID field. So it looks a bit simpler in the union. And yeah, I think that's it. Yeah, and so the reason why I'm kind of talking about this, there's this study that was performed some years ago. It looked at Ruby on Rails and Django applications, and it analyzed the performance issues, and it came out that the missing database indexes was the #1 problem. It scored 30 in their like score sheet. To be completely honest, they also had like n+1 queries, which scored 29, so just 1 less than the missing indexes, but the missing indexes was the major like performance issue with the applications that are based around ORMs. So yeah, just a conclusion. So when programmers write code, I usually advise not to optimize ahead of time. So in the kind of database, it would be like creating indexes for every single field you might need to query. So instead, you can use like, once you have the queries, you can explain plan and let this explain tell you what kind of indexes database is actually looking for, and then create the indexes as you need to. So that's all.
I have a question. Which chocolate do you prefer, dark or milk?
That's a minute.
Milk.
Milk. So
I prefer dark one, but my wife will be happy about milk.
Yeah, okay. Do you have any other questions?
Regarding you so told that Postgres SQL and MySQL are storing the different data, so MySQL is storing the whole row in
Yeah, index.
like index, and it is related to all engines, or it is related to my standard default, or somehow there are engines that acts like.
Yeah, I think it's like InnoDB, so they use this kind of B tree as the main storage, and then the kind of what you call secondary indexes are like really secondary indexes because they contain like key and the value in the primary index. So you, yeah, so here it's more like, it's a bit more similar to what Oracle has like by default. Yes?
One question about explain and explain analyze. So you said that explain analyze actually executes the query.
Yeah.
Can it be done only on select queries, or can it be done on update queries as well? For
Yeah,
example?
on update, yeah, as well.
And it will actually update the row in that case. if
Well,
it's-
I haven't done that. So most of the time it's kind of issues how it selects. I guess it should. There are other options, like you could specify that you want to have like, there are like options you can, what people typically use is also ask for buffers information. So yeah, it will tell you how much it hit through the cache and how it actually read from the disk. You can also ask for write ahead log. So in case of updates, it will say that, oh, I wrote this many blocks to write ahead log. But to me, it's more like for like DBAs, because as a developer, I can't use that information.
But would it be the right tool to investigate why selecting rows for update in a table is causing log contentions, or are there better tools to investigate something like
For
that?
log contentions?
Yeah.
No, for log contentions, I would look at the logs. So, I mean, that's a bit more different topic, because like, are you talking like Postgres table?
Yeah.
Yeah. I mean, typically what I do, so there are, if you like Google, you can find queries how to check out the logs. Most of the time for me, it's like, try to avoid like long running transactions, and there are some, I don't know where to start. So Postgres has like, I don't know, log contention, typically I see those like when database migration conflict with you.
Yeah.
It's very hard to run like database migrations in the running system in Postgres. So that's the, just like pure log contentions. I mean, you look up the logs and you see on which tables, and you can kind of figure out like what's happening there.
So it's more of actually investigating your application's behavior instead of just asking the database why is it
Yeah.
happening. Okay, thank you.
So only 2 people understood something what you were. Then, thank you very much. For your help.
Oh.